For those who don't know me, my name's Roger Dimmock, and I started and now run the BAA's Exoplanet division, which is part of the Asteroid and Remote Planet section. Welcome to this meeting, and apologies for not running the last meeting, but we couldn't get all the speakers lined up. And we've had some problems with this one, as I will explain later. Anyway, thanks to Callum for looking after us, for Rodney for keeping me in line, the speakers, and all of you are attending. Right, once upon a time, there were just transits. There's so much more to be learnt from them, hence the title. For those of you who are old as I am, this is the original transit, 1965. Now, there won't be many people out there who, like me, were around at this time. And I guess most of Rodney's young Open University guns were not there. But anyway, that's the original one. That's 60 years old, would you believe now? Right. This is the agenda. Much revised, I'm afraid, as our first speaker, Peter, was in hospital for 3 days this week and feels too ill to give the presentation. But just discussing with Callum, we may try and arrange for him to record, and then we can put it on the BAA website. But there you go. My introduction, recap on TTVs for those who may be new to this, and those who, like me, are so old you've forgotten some of it. Anyway, then we have Paul Dooley, exoplanets orbiting non-eclipsing binaries, lunch break. Then Rodney will look after the afternoon with Daniel and Asher Kumar, if I'm pronouncing that correctly. And I'll come back at number 11 with a little bit about the Kepler 88 system. And I'll try and give you a brief introduction to Exoplanet Pi. Right, just some admin. Would speakers like to say a bit about them at the start of the talks? Is less complicated than me doing it. Questions, the chat facility, but I think we can use other aspects, so chat mainly, I think. Presentations will be recorded and put on the BAA YouTube channel. And could I please have a PDF of your talk, if possible? It will help me when I'm writing up the meeting. If you don't want the recording or et cetera, please let me know. Right, running through briefly then, exoplanet transits and introduction, variations, some of the observatories involved, and then hopefully those who are new to this will have a basic understanding of transits. So what's it all about? As I said, it's a recap for some of you and maybe new to others. So I'll look at single planet transits and multi-planet transits and what they can tell us about the orbits of the planets and the planets themselves. Passage of a planet in front of its host star can be referred to as a transit or a primary eclipse, although we tend to use transit. When the planet goes behind the star, it's referred to as an eclipse or secondary eclipse. These are much less deep than the transits are much less deep than the primary transits, but they can be detected. When a planet passes directly between a star and its observer, it dims the light by a measurable amount, and you don't need a very large telescope. You can do that with a 6-inch telescope. Obviously, larger planets block out more than the light, and which is why discoveries have been skewed in that direction. Many more large planets than Earth-sized small planets. You can see the effect of planets of different sizes and the changes in the light curve. So as I said, you get a deeper transit with a larger planet. That's why many more of them have been discovered. Light curves get complicated when more than one planet is transiting a star, as this animation will show. The light curves can give us the same information as a single one, for the combined star planets, that is. Just takes more work to pick out each planet from the data. So you can see you may get a separate dip for each planet, or you may get a combined dip when both planets are transiting. If two planets are in a mean motion resonance, That is, the orbits are a simple integer ratio of each other. The larger can influence the orbit of the smaller by changing its eccentricity or period or inclination, which can lead to changes in transit timing. These are example observations using the Free Micro Observatory based in Arizona, which is just a 6-inch telescope. And a plot from the Exoplanet Transit database is on the left and the Exoclock database on the right. It's worth pointing out that Exoclock no longer accepts observations from public observatories such as this, as it was felt to be confusing if the same data was input by different observers. But as you can see, with a small 6-inch telescope, you can see a transit quite easily. Key transit measurements are the transit duration and the depth. And obviously, if you see more than one transit, then the time between transits is important, as that gives an indication of the orbit of the host star, of the planet, I should say. Determining the time between successive transits will define the orbital period of the planet. That's the green path. Knowing the mass and diameter of the host star gives us the planet's semi-major axis. That's both the yellow and the green paths. Magnitude drop in and out of transit, from which the related flux ratio can be calculated, combined with knowledge of the host star's diameter, will enable the planet's diameter to be calculated. That's the red path and the yellow. There have been some problems with this, as the diameters of many host stars were found to be incorrect. So we were getting incorrect measurements of planet diameters. This video shows how transit times vary when a second planet is introduced into the system. Initially, we see a single planet with the transit times indicated when the timer on the right shows 12 o'clock. And we get to a two-planet system with the additional planet in a wider orbit. And the mid-transit times can be earlier or later, depending on the relative positions of the two planets. The effect of an additional planet, an actual example. The transit time in variations of KOI 872b, shown on the left, these here, led to the discovery of planet C, a non-transiting binary. And there's possibly a third planet in the system. So TTBs can lead to discoveries, very important. On the left image, which I mentioned earlier, we see a exoplanet transit and a secondary eclipse, which is much smaller. On the right image, a non-transit exoplanet, no transit, due to the inclination of the orbit with respect to our line of sight. As on the left image, we see variation due to reflected starlight. That's the composite curve here. And maximum brightness at superior conjunction, that's the star plus light reflected from the planet, so that will be here. And minimum at inferior conjunction, and there's no light reflected from the planet. A paper titled Follow-up of Non-Transiting Planets Detected by Kepler describes how the authors searched the Kepler database for such variations and actually discovered 3 hot Jupiters and 3 more planets. So even when you don't get a transit, you can still discover a planet. Another example of TTVs leading to a discovery, the first detection of a non-transiting planet using transit timing variations was carried out with NASA's Kepler telescope. The transiting planet B showed transit timing variations indicating the presence of a second planet C, which has a period that is in a near 3-to-1 resonance with Kepler B. Planet D was discovered by the radial velocity method. That's measuring the wobble of the host star due to the gravitational interaction between the star and planet, both revolving around a common center of gravity, the Barry center. Kepler and its follow-on mission ran for 9 years altogether. Transit timing variations can also be used to measure the mass of exoplanets in compact multi-planet systems such as TRAPPIST-1, I should say. This slide compares the TRAPPIST-1 system with the positions of the inner planets in our solar system. So TRAPPIST-1 is located at La Silla and is operated from a control room in Belgium. TTVs can also be used to measure the masses of planets that are in 2 to 4, 6 to 9, or 2, 4, 6, 9, 12 resonant chains. The system TOI 178 is an example of this. TOI stands for Test Object of Interest, and you'll come across quite a lot. So TESS is going to be busy surveying 200,000 stars. And as I say, the TESS Objects of Interest catalogue includes both new planet candidates found by TESS and previously known planets recovered by TESS observations. The vertical axis shows the change in transit times, negative indicating transit times are earlier than predicted and positive indicating they are later. For this particular WASP-12b, the change is approximately 8 minutes over 10 years. It may be a decaying orbit, but it could be an eccentric orbit as well causing this. Another paper concluded the variations are due to planetary-induced slides in the host star. If the eccentricity is known, this may indicate whether or not the variation is due to that. So you can see the change in the orbital period there. Is an example of transit orbit variations. The orbit is precessing anti-clockwise, so it's going that way, and the planet is in a clockwise orbit going that way. The sequence starts with the planet that is furthest from host star, Zapastron, and in the top row, as the orbit precesses, the transits become later, as the planet has to travel slightly further for the transit to be viewed from Earth. And in the bottom row, the planet transits earlier than expected, but less earlier as the orbit continues to precess. Of course, the orbit can also experience changes in its shape, more to less elliptical. Nodal precession is when the ascending and descending nodes precess as shown here. This is the descending node and the ascending node. Hot Jupiters are in tight orbits around their host star, and since that star will not be perfectly spherical, small gravitational perturbations will cause the orbit to precess. When the Earth exoplanet host star lined up as shown, we would see the lower transit. The effective precession of the nodes would cause the orbit to move as shown by the shorter dotted line. An example of this is WASP-33b as indicated in the diagram on the right. I've oriented that to line up with the diagram on the left. And you can see that the change in the transit there. The impact parameter varies from 0 when the transit crosses the center of the stellar disk to 1 when the transit crosses the edge of the disk. And the transit duration also varies with the impact parameter. It will be longer at the center of the disk and shorter at the edge of the stellar disk. The light curve of comets is very different from the usual U-shape associated with exoplanet transits as shown in this diagram. This is a typical comet transit, and it was taken from comets around Beta Pictoris. Can have exotrojans too. The positions of trojans are shown in the diagram on the left, and the ALMA image shows the planet and another object which could be a Trojan, a clump of matter condensing into a planet, or planetary debris. You can get variations due to exomoons, but I don't believe as of this time any exomoons have actually been discovered. Hubble and Kepler observations have uncovered evidence of what could be an exomoon. But to say whether or not it's actually a moon is as yet to be decided. So we have a planet followed by a moon, and you can see you get a little dip at the end of the transit. This is a light curve of two transits with a leading solid line and a trailing moon, the dashed line. Where the moon is leading, we get the solid line here, followed by a slightly deeper transit, and then the solid line there as the transit ends. Where the moon is trailing, we get the dotted line, where we'll see a slight change in the transit at the end of the main transit. You see the moon only is just a shallow transit. In the left diagram, the moon is leading the planet. You just see that there. In the right diagram, the moon is trailing the planet, and we get a slightly deeper transit there. Not easy to see. Transit depth variations. The planet appears to have a larger radius shown by the deeper transit when imaged in red light than in blue. A star is not the same brightness across the diameter of the disk, known as limb darkening. The image of the sun and the light curve below show this effect. Imaging at shorter wavelengths leads to stronger limb darkening, and measurements of the transit at multiple wavelengths, as you can see here, allow the amount of limb darkening to be defined, and this is subsequently used to accurately determine the radius of the transiting planet. Another observatory, convection, rotation, and planetary transits. And this observatory was used to observe the various depth variations shown in the previous slide. Stellar variability can also cause problems with measuring transits. A large spot will give you an incorrect measurement of the planetary radius, and it may also lead to a false exoplanet detection. But star spots rotate with a star and cause relatively slow changes in the brightness, whereas a transiting exoplanet crosses a star in a much shorter time. So it should be relatively simple to sort those out. The right-hand diagram here shows Kepler 3c, and a portion of the light curve is shown below. The black line B is a transit as it would be without the star spot, and the red line indicates where a transit with one spot. I showed the left-hand diagram earlier, and it may be that there was a star spot involved in this particular light curve of Coro 3b. This is where it all started for us with the Exoclock project. Back in the day, just before COVID struck, we had a presentation of the Exoclock project, an asteroid and remote planet section meeting. This was in the nature of a pre-announcement that hadn't yet been revealed to the rest of the world. This project was the main driver and remains so to keep this division going. But we've one or two other interesting things coming down the pipeline. The exoplanet transit data will ensure that the aerial spacecraft is pointing at the right star at the right time, as we have noticed looking at a lot of the data we get that the orbits are varying and not quite where, and it would have meant if without the exoclock data that Ariel could have been pointed at the right star at the wrong time. So this exoclock mission is extremely important to Ariel. And here's some of the planets that exhibit TTVs. You can find them on the Exoclock website if you want to try your hand at this sort of thing. The Kepler 18d is fairly obvious, and the transits are varying in a cyclical nature, as you can see here. So I've given you a glimpse of the multitude of variations, but I'm going to leave it for clever people following to explain some of the various mechanisms and how they can be detected and analyzed. Right, we had Peter and Paul to begin with, but unfortunately Peter is can't be with us due to 3 days in hospital followed by illness, and Paul will follow on from me and say a little bit about where all the Tatooines have gone. And I'm afraid Mary too is no longer with us. I think actually Paul is the only one of the original trio who's still with us this day. Right, folks, that's the end of me. Moving on to the next one.
You've unshared, Roger, yeah?
Yeah, I've unshared, yeah.
Okay.
And after Paul's presentation, we'll take our lunch break.
Just bear with me a few minutes while I look at what I'm doing. Share screen. Right, am I back in?
You're in.
Right, lovely, thank you. So I just had to come out and go back in briefly there. I'm just going to share my screen now. And hopefully...
Looks good, yep, that's fine,
that.
well done.
Okay, here we go then. So my name's Paul Dooley. I've recently completed a Master of Physics qualification at the Open University, specialising in astrophysics and space science. Excellent course, can recommend it. It's taken me 11 years to do it, but I've got there in the end with some excellent guidance from our own Rodney. As part of that course, a dissertation was required, and I elected to have a look at a subject area involving non-eclipsing binaries and exoplanets in non-eclipsing binaries. This was a particularly interesting area to take on because there seemed to have been very little work done in this area in recent years. So I thought this was a good one to pursue. So that was the subject of my dissertation. And this presentation is largely based then on that premise. So moving on. So if we think about the stars we see at night, we tend to see little dots, but in fact, an awful lot of these are binary stars, and the amount of stars that we see that are actually binary stars is estimated to be anywhere from 50% up to 85%, depending on whose papers you read. but certainly there are an awful lot of them that appear as single spots to us are in fact binary stars. But if we think of the orientation of the orbital planes of these binary systems, you would think that perhaps they would be aligned with the galactic plane, but it turns out that pretty much they're not. They're pretty random. So if you're looking for binary stars and perhaps trying to detect them by the fact that one is going to eclipse the other, a bit similar to the way an exoplanet would, um, what we see is actually most binary systems won't eclipse. So there'll be an awful lot out there that aren't obvious. Exoplanets have been detected around binary stars, but most of them would be around eclipsing binaries because these are the ones we know about. So we've got a bit of a selection effect there. So I came across, excuse me one moment. I came across in the course of my studies, I'll just mute my microphone and have a cough. Yeah, that's about it. Yes, in the course of my studies, I came across a paper by Martin and Trio, written in 2014, that really addressed this whole subject of why were we not addressing non-eclipsing binaries, and that perhaps there were a lot of exoplanets we were missing because of this. When we talk about binary stars, we have to be a little bit careful as to how we classify them. Traditionally, we classify binary stars by their detection methods. We talk about a visual binary, which is a binary we can actually resolve with a telescope. Spectroscopic binaries are detected through radial velocity measurements. Astrometric binaries are detected through the motion for the one star affecting the other. So even though we can't see both stars, we can infer one. And of course, photometrically, as with exoplanets, we can detect transiting eclipsing binaries, and those are quite easy to see, as we'll see. I've put in as well in brackets gravitational microlensing. Not really heard too much about that in terms of binary stars. It's certainly a method we can use to detect very long-range exoplanets, but it's not really one we use to classify them. If we think of other ways, excuse me once again, I apologize. I've got a bit of a throat today. That's better. Right. Thinking about other ways we can classify binary stars, and we can classify them by their proximity, and we can talk about close binaries or wide binaries. And this is another slightly arbitrary distinction in that, again, depending whose paper you read, you might say that a wide binary had a semi-major axis greater than 50 AUs or 100 AUs, or in one paper I found it was 700 AUs. It really depends on what the researcher is trying to prove, I guess. But certainly the close ones are ones which affect each other, not just gravitationally, but in terms of their common envelopes. And we'll look at that in a moment. The final way is by orientation, and this is where, again, we make the distinction between an eclipsing binary and a non-eclipsing binary, and that's where geometry comes in, and I'm hoping that's what I'm going to show most of today. Just thinking about eclipsing binaries, just to make sure we know what we're talking about. Again, this is very similar to a transiting exoplanet. So what we've got is the orbital plane of the binary system is aligned or close to aligned when viewed from the Earth or the environs of the Earth. So you'll get a flux reduction overall from what you're seeing as one star passes in front of the other. And we can pick this up quite nicely photometrically. And there's a nice little diagram from a paper by Hani et al. On the right there. So we can really define our non-eclipsing binary basically as one that doesn't eclipse. As simple as that, really. So that's a very simple distinction for us. Looking at the close binaries, just to cover that off, these are the ones which do influence each other, not just gravitationally, but in terms of their envelopes actually interacting. And we can talk about three types. A detached binary, where they're very close, but the envelopes actually, the stellar material is within what's known as the Roche lobe. And the Roche lobe is the sphere of gravitational influence, but where all the matter associated with that star is going to remain with that star. Once they start to get closer to each other, a semi-detached one, they're actually close enough now that one of the stars will overflow its Roche lobe, and matter can actually be transferred to the other star. And we see that with things like cataclysmic variables as well. And ultimately, if they get close enough, but without actually fully merging, we'll have a shared stellar envelope. So the outer material of the stars will actually be shared. Again, another paper worth looking at there is Tyrrell. All these references, by the way, I've included on the slide at the end of the presentation. So if you do take a copy of the presentation, you can look at those to your heart's content. When we're looking at the close binary stars, I've said P-type is more likely than S-type, and I realise now that I haven't introduced the concepts of P-type and S-type yet, so my apologies. That's actually coming. But the P-type are where a planet orbits both stars, and S-type is when it's only orbiting one. We'll look at that shortly. One of the things, again, during my studies, I came up looking at classifications, is you do have to be careful because these classification systems overlap, and which method you choose to classify really depends on what you're trying to achieve. So, for example, a visual binary, one we can resolve, well, that surely depends on the power of your telescope. And as telescopes improve, more and more binaries could be classified as visual binaries. Many spectroscopic binaries are also eclipsing binaries. The close binaries are also more likely to be eclipsing, and contact binaries, unless you're going to view it from exactly above its orbital plane, is probably going to eclipse as well. And when we talk about non-eclipsing binaries, all these can be included. So you just got to apply a little bit of caution when somebody says this star is eclipsing or this star is spectroscopic. It might be both. So now we'll touch on the types of exoplanets. I perhaps should have put this slide in earlier, but what we're going to look at is the three types which a guy called Dvorak, or possibly Dvorak, I'm not sure, not the composer, put together in 1984. And he came up with three categories of exoplanet in binary systems. The circumstellar, or the S type, is the exoplanet that orbits a single star within that system. The circumbinary, the P type, is orbiting both members of that binary pair. And there's a third type he specified called the librator, or L type. And that's where the exoplanet is orbiting either the L4 or L5 Lagrange points, as Roger showed in the slide earlier. As far as I know, there are no L types have been discovered to date. Certainly not in my research. I haven't found any reference to them. So we're just going to concentrate on S and P type for this lecture. Not every possible configuration can exist out there in terms of exoplanets in binary systems. There are areas of stability and instability. Again, a very useful paper to look at that is Musilek et al. And they looked at two things in particular: the ratio of the masses of the two stars and the ratio of the distance of the planet to either the primary star or the barycenter of the stars, and the distance between the stars themselves. And for both S-type and P-type, they came up with ranges of stability and also some areas where things were, they called it marginally stable, which I guess means it could go either way. If we look at how many exoplanets around binary stars we have, I did a quick check yesterday on the exoplanet.eu, the Encyclopedia of Explanatory Systems website, and they're currently listing a total of 7,415 exoplanets, and that goes up daily, I think. But of those, there are a couple of subtables that show 232 S-type exoplanets and 29 P-type. So very much the more common are the S-type exoplanets. As part of my project, I wrote a little bit of Python code which cross-referenced these stars with a number of other databases. Simbad, probably aware of, is a very popular astronomical database. The Gaia mission, Data Release 3, has some lists of what it calls non-single stars. And Kepler has an eclipsing binary database. So by cross-referencing all these and using a premise which was a bit of an assumption, but I thought a not unreasonable one, that if it wasn't shown to be in any way eclipsing, it was probably non-eclipsing. That made 216 of those exoplanets come in as non-eclipsing, and only 2 of the P-type. So been very interesting to look at Gaia data, and I strongly recommend anybody who wants to look into some really excellent data now being produced, have a look at the Gaia website. A lot of further research, I think, is needed there to really say what's the significance of this. Is this a selection effect, or is it something more fundamental going on? So starting to think about the geometry of these systems now, this is just a very simple set of perspectives, really, of 3 potential situations, looking more at the S-type at the moment. So if we think of how from the side, an eclipsing coplanar, so this is an exoplanet in orbit around one of 2 stars, but its plane of orbit is the same as the plane of the stars. We can see the view perspective, we will get transits in that situation, and we should be able to detect those transits. If, however, it's a non-eclipsing star from our perspective, and the orbit is still coplanar, we probably won't see that. So that's much harder to detect photometrically. It can be done through reflected light, but not through a transit technique. If, however, that exoplanet was on an inclined orbit, in other words, its orbital plane is at an angle to the plane of orbit of the two stars, then once again we might detect that photometrically. So that's a really interesting thought, that maybe if we are detecting photometrically around a non-eclipsing binary, that probably implies we have an inclined orbit, which is further data on that planet. So, not as part of my project, but it's really a couple of years before I was working with Rodney on assisting my son with his project for his master's degree. And just for an exercise, I decided, wouldn't it be interesting to write an N-body simulator? And this was inspired really by Rodney, who had produced a fairly simple but very effective simulator using Python that just showed a simple three-body problem using integrating techniques. So it doesn't solve any differential equations. It just works out the forces between three bodies, moves on a small time step and sees where they move to and keeps going round. So I decided I was going to write my own. And at the time, having a background in systems programming and being retired, I was in the mood to learn a new language. And I'd come across Rust, which seemed to be gaining traction in systems programming circles, and people like Microsoft and so on were looking at this. And it was seen as a very robust language that could be used to write core systems and kernel code in a very safe fashion. But any language can be used for scientific applications. So I started having a look at that. So I rewrote this simulator Rodney had started with using Rust. I'm a Linux user, so I wrote it using Linux, using GTK as the graphical interface and OpenGL as the actual display. I did try and get it to run on Windows. The port was proving quite difficult, so in the end I abandoned that because I really needed to concentrate on my own project. But this was useful during my project just for visualizing some of the scenarios that we've been talking about. Fairly simple interface, as you can see, and it just allows you to load up simple configuration files and run simulations. The internal logic, excuse me again, is fairly straightforward. So all we need to do is specify for each of the bodies in our simulation how big they are, mass, initial position, and velocity. And we can do these in terms of 3D vectors. The software then draws an initial scene. We calculate the net acceleration on each body due to all the other bodies. And using that information, we can update the velocity of each body. And then apply that for a certain time step will give us a new position for each body. Then we redraw the scene and start again. And how accurate our simulation is depends on factors such as how small our time step is and what other effects we take into account. So, for example, there's no relativistic effects in my simulation. It is purely working on straight Newtonian mechanics. So for the second half of this presentation, then, we're going to look at some simple simulations and talk about those a bit. I'm doing this in real time. They're not pre-recorded, so bear with me. If you have a slow internet connection, I apologize if it seems a little jerky. I've tested it in a session with myself on a different machine, but I've got a very fast internet connection. I'm running a gigabit internet connection, so it may be that it looked better for me than it will for you. So I apologize in advance if it's a little jerky, but we'll see how it runs. So the first one I'm going to look at is a simple binary system. So I'm just going to switch screens now. And hopefully, if somebody could confirm, maybe Roger, that we're seeing the planetary system simulator window.
Yep, you're okay.
Good.
Go.
Thanks, Rodney. Brilliant. So for the first one, I'll just use this menu, and I'm just going to I'll just close that. I'm just going to load up an existing scenario I've pre-configured. These are text files. They can be produced by the software, or you can manually edit them, and it has a certain number of keywords which define the system. So we'll just load that first one up. I'm going to run that simulation. And all I need to do is make it bigger. And what we're seeing initially here is a top-down view of just a binary system. So I've got no exoplanets at this point, and hopefully you can see those nicely rotating. I can put some names on them to make them a little bit more obvious. And we could add an orbital trail just to see how they're orbiting around each other. And I could even put on a barycenter. So that's the barycenter of the system. Okay. I have a set of axes, which are red, green, and blue. So we're now just looking top down, and we can rotate the image and we can start to see how this looks from different perspectives. If you really like it, you can add a little star field at the back, but for this purposes, I'm going to leave that switched off. So that's our simplest system. Now, as we've got it, the angle I'm looking at it, it's a non-eclipsing system. But if I look at it from a different angle, it would become an eclipsing system. And where we draw a light curve here, we would see, hopefully, a sort of light curve we'd expect to see. We do have the ability to draw a light curve with this software. It's fairly simplistic. It really gives you the form of the light curve only rather than the detailed shape. There's no limb darkening allowed for, but it's quite useful. So this is what I call the composite light curve. Just going to put it on top. And hopefully we'll see as one goes in front of the other, we get a dip. And I can just change the scale on that one a little bit. So we'll see a little bit more obvious. So that's the sort of dip you might see in an eclipsing binary situation. And if I just go back to it non-eclipsing, then obviously we'll see no dip. So that's just making sure we understand really the principles of the eclipsing versus non-eclipsing situation. So we'll come out of that. I'm going to quit the interface now, and subsequently I'm going to use command line interface because it's just slightly quicker. So hopefully we've got another window up there now. So this is our second scenario. I'll just go back to my slides. So the second one we're going to look at is a wide binary system with an S-type exoplanet on a coplanar orbit. So this is the first of those three scenarios we saw in the earlier slide. So again, let's just draw some orbits, and we'll start to see the sort of orbital tracks we'll get as the exoplanet is orbiting around one of these two stars. I'll just speed up the simulation a little bit. And anybody who's ever played with a spirograph will understand this. But it's very interesting, the sort of trail that you would get. So this is viewing directly towards the barycenter again. And once again, we can look at this from different angles. And this is purely being done by recalculating each step using standard Newtonian mechanics. So I'll just take that off a little bit. What we're going to do now is have a look at a light curve here. And my default is a little bit low, so let's just change that. I need to make that always on top. So again, we're looking at the composite light curve. So we're looking at the light from the whole system, because it's quite possible that from our Earth perspective, we'd be only seeing one light source. So let's now start having a look at what we might see here. Again, I'm just going to stretch out that time base. And you can see we're getting some dips now from the exoplanet transit, and then a much bigger dip when we had the star transiting. So this is what we might actually see on this kind of scenario, where we actually have combinations of small dips due to an exoplanet transit intercepting large dips at various points. Again, we'll just speed that up a little bit. I think that shows that quite nicely. That's orbiting quite quickly now. I'll just slow that down a bit more. So if we take this now to be non-eclipsing, there comes a point where we will no longer see any transits, either for the exoplanet or the star. Now, the angle at which that occurs is subject to a number of factors to do with partly the distance we're viewing from, distance between the stars, and so on, distance the planet is from the star. That's an area which I really hope to do some work on in future to come up with some formulae that could actually calculate those, because it's just geometry. It should be fairly easy to do. Okay, so that's the simplest one of those. So moving on, the next scenario I'm going to look at is the S-type again on a wide system, but this time we're going to incline the orbit and see what difference that makes. Now, depending on how the longitude of the ascending node varies, this can actually produce quite a few different scenarios. So Unfortunately, can't look at everything today, but we'll see what we can see. So let's fire that up. Right, so again, this is the top-down view. Again, we'll just put some names on there so you can be absolutely sure what's what. I'm going to draw the orbits, and then we'll tilt the system. Now, the difference this time, as you can see, is that exoplanet is on an inclined orbit. So with relation to the orbital plane of the system, we are orbiting at an angle. So let's have a look at a composite-like curve for that one. Let's change this default to something bigger. There we go. So at the moment, at that particular angle, we are getting, speed up a little bit. Bring that back. I'll just make that always on top. Go. So this is clearly now a non-eclipsing binary system. But if we get the angle just right, we will still start to see some exoplanet eclipses. So that's really showing that with an inclined orbit, we are possibly going to get some exoplanet eclipses. I'm just going to redraw the orbits now. I think it gets a little bit busy. Again, depending on our observational angle, we'll see more or less transits. At the moment, that's nothing. There we are, starting to get some transits appearing now. So with this tool, we could really explore this from every possible angle. And we can even roll it on quite quickly into the future and check on things like orbital stability, but that's a little outside our scope today. Okay, so we'll come out of that one. So I've just got a few more scenarios to go through before we break. Next one is going to be a P-type exoplanet. So this is going to be orbiting both of the stars. These are really the Tatooines we're talking about. These are the more interesting ones, I feel, to an extent. With the S-type, they're not a lot different from an exoplanet around a single star. But the P-type ones, I think, coplanar, are really quite interesting. So this is going to be on a coplanar orbit now. So let's have a look at that one. So again, I'm just going to put a name on it. I will zoom in a bit because that's not looking very obvious. Now, this is a top-down view again. So here's our orbital paths. Speed that up a little. So we can see we've got a nice pair of stars, different masses this time, just orbiting a common barycenter. Let's put the barycenter on. There it is. And we've got an exoplanet in orbit. And if I just tilt it down by 90 degrees, you'll see it's a coplanar orbit. So it's in the same orbital plane as the stars. But I want to leave it on the top-down view for the moment, because what's interesting now is because of the interaction between the exoplanet and the combined gravitational effect of both stars, we're seeing a precession in the orbit. And this is something that's been predicted in a number of papers again. So when I first wrote the software and started to see this, it was a nice validation of the code I'd put together. And we leave that running long enough, that'll just keep changing that. Okay, so we'll start from the beginning again. I'm just going to slow it down again, and let's look at a light curve for that one. So at the moment, we've got a non-eclipsing system, and unsurprising, we're not really seeing any eclipses. Let's put the orbits back on there. If we make it an eclipsing system, we're going to see some interesting effects. Because really, what we'll tend to see is a standard sort of binary system, like two different dips, because we've got different sized stars. But occasionally, there we go. I think it just occurred there. I'll just slow that down again. Occasionally, we'll get another dip due to the exoplanet passing in front. And again, mathematically, it's quite hard to describe that simply. But depending on the exact orbit, you should be able to detect an exoplanet by the fact that there are some dips where they shouldn't be. So you're detecting a standard binary system light curve, and then sometimes those dips get corrupted. But it's not on every orbit, you'll notice. It just depends whether it's aligned at the time. So a lot will depend on the semi-major axis of the exoplanet's radius of orbit. And then we'll go back to a non-eclipsing situation, and sure enough, we will lose any possibility of an eclipse in that situation. Okay. So just a couple more to go now. The next one we're going to look at is, as before, we'll look at the same system, but we'll incline the orbit of the exoplanet now with respect to the orbital plane of the binary system. Just bring that one up. Again, we'll look at that from a top-down view. Looks fairly much as it did before. Again, I'll put some names on those, but let's now look at it from a side view. So now we've got an inclined orbit. You can see these orbits for these p-types are generally very wide because a close orbit would not be stable, and that was covered on that earlier slide. There's too much gravity going on in the middle, and it's too chaotic. So generally, these orbits are quite wide, but it is orbiting the barycenter of that system. Okay, we'll just zoom in a bit on that. There we go. So again, we'll look at a light curve for that system. Let's move that out of the way. Move that across. Make that always on top. Let's make that bigger. So at the moment, this is a non-eclipsing. Now let's make it an eclipsing system. There's an eclipsing system in terms of the stars. And sure enough, we're seeing the light curve we'd expect to see from the stars. Now, a lot of the time, we won't see anything from the planet. Depends what orientation. So again, this is very much dependent on the longitude of the ascending node of that exoplanet with respect to that binary system. And now we will see some additional effects due to the exoplanet. So we're seeing some smaller dips there interspersed with the larger dips. So again, from a practical sense, it's all about differentiating the exoplanet flux reductions from the binary system. And obviously, using modern software, you can remove those binary system flux changes and just see the exoplanet dip. So I'll go back to the non-eclipsing situation now. And we can just about see that there are situations where in a non-eclipsing environment, we would see some exoplanet transits. However, due to the precession of the orbit, it won't be forever. So it'll be for a limited period of time. So it may be that you manage to catch serendipitously an exoplanet just at the right point and think you've discovered something amazing, and you probably have. But in time, those transits will disappear. So inclined orbits give us more opportunities, but not necessarily for very long. So just two more scenarios I want to show you now. The next one is going to be a particularly interesting type of P-type exoplanet, which is in a polar orbit. So by this, I mean it's in a polar orbit around the barycenter of the stellar system. It's a stable configuration. They should exist on the basis that pretty much space is big enough that anything can exist, probably does. I'm not sure whether any have been found as yet. Probably not. So again, that's the top-down view. Let's name our bodies. Just make them a little bit bigger. There we go. And it sort of looks like the exoplanet is moving out and back in. But I'll draw the orbits and then we'll tilt the system, and you'll see actually what we've got is exoplanet in orbit around the whole system, and it's in a polar orbit around the barycenter. So I think that would be a really interesting one to find if we can find that. And really now, whether it's eclipsing or non-eclipsing will only affect the light curve in terms of the the stellar portion. What's more interesting is whether or not we can view it from an edge on to the exoplanet orbit. And again, that will now very much depend on where in the orbit. Let's just make sure that's non-eclipsing. And on top, I'm just going to speed that simulation up a little bit. So we're getting occasional transits now as it crosses in front of the orbiting stars in that binary system. Once again, you can see there's a precession starting to build in, and it seems to be common to all orbits around binary star systems of the P-type orbits anyway. If we get another one. There we go, that was a big dip. And if we make the star system eclipsing as well, then we'll start to see the stars. And I'll just increase the time base there a little bit, which will smooth that out a little bit. So those are the stellar flux changes. And then I think there was a little dip there that came in from the planet as well. So that's a really interesting one, I think, to look at, and probably wants further exploration. So just to finish off then, I'm just going to look at another scenario. A lot of people might question, how do you get an inclined orbit when most planets are formed from a planetary disk and will normally be coplanar with the stellar plane. However, we can imagine other means of this happening. One is something called the Kozai-Lidov mechanism, which is a resonance where large planets in outer orbits can migrate inwards. This is possibly what's happened to a lot of Jupiters we found out there, and doing so might perturb the orbit of another planet, putting it into an eccentric orbit or an elliptical, an inclined orbit, I should say. Another is the concept of a rogue planet. We think there are actually many rogue planets out there. This is a planet that's possibly been ejected from its stellar system and is not bound to any particular star. And you can conceive that even in the vastness of space, that over time, it's possible some of these rogue planets might enter a stellar system, be captured gravitationally, and either join it or perturb it. So we're going to have a look at a simple scenario there. It's not a great simulation. I spent a lot of time last night trying to put this one together. I couldn't quite get it how I wanted it, but hopefully it will get the point across. So this was my second attempt at it. So I'm just going to stop the simulation there. It looks very small because we're looking at quite a big system right now. So what we've got here, I'll zoom in initially on the star system. We've got two stars, different masses. So that's our stellar system. And then a long way out, we've got a rogue planet, which is on a different trajectory. It's actually going to pass to the side of this system unless something else happens. Okay, so apologies, it's going to start small, but as we roll the simulation, I'm going to zoom in and hopefully you'll start to see. This planet is already beginning to curve as it's starting to get the influence of the stellar system. There it is. It's just coming in on the edge of the screen now. What I can do also is we can have a look at the information about that exoplanet. I'll just stop it there. So the rogue planet is a 0.33 of a Jupiter mass. It's got a radius of 0.75 Jupiter radii. I've given it a temperature, and we can see its distance from the center, excuse me, and its current velocity. And what I want you to notice there is the velocity is increasing. Okay, so this is the magnitude of the velocity. So that's a speed. And as we get closer, again, we'll start to zoom in on this a little bit. You can see it's now going to start getting captured gravitationally by this system. Speed it up again. The only limitations on the speed of the simulation are partly down to processing power, but also your graphics card, what sort of frame rates it can make. So initially, it's just gone into what looks like a hyperbolic trajectory. But again, we'll just roll that on a little bit quicker. Zoom out and move that again. A little bit faster. What we're going to see, hopefully, it's going to come back in. Just need to change another couple of parameters to speed that up. There we go. So we now have an orbit. Question is this orbit stable? Well, it's certainly not particularly consistent at the moment. Over time, again, I'm going to roll it a little bit quicker just so we can see what happens. See, we start to get some straight lines on the orbital plot now as I roll on too fast. Just because it's not plotting continuously, it's plotting at every time interval. But it looks like it's, although it's changing, it's not going to eject the planet. And I'm just going to go absolutely breakneck speed now just to see how this orbit develops. Okay, we plot a total of 4,096 orbital points, which is why now the tail end of the orbital path is shortening. And I ran this last night for a couple of hours, and it precesses and migrates a lot, but it stays in orbit, so it is stable. So that's an interesting way to explore perhaps how a rogue planet might be captured by a stellar system. Now, there's nothing to stop with this software. You're putting in more planets and seeing how they affect it. All you need to do is specify these initial conditions of size, mass, velocity, position. Future enhancement, I hope to be able to do it a little bit more graphically, where you can just click a mouse and define a new body on a live system. But unfortunately, that's a little bit beyond me at the moment. Okay, this orbit's getting quite interesting now. So I think we'll leave that one there. And that's pretty much the end of the scenarios. So just to give you a few comments to take home. So really the main thrust of what I've been talking about here is how geometry does affect how we can detect, certainly photometrically, exoplanets orbiting binaries. If we do detect one, then there's a good chance it's on an inclined orbit. So that's extra data we have. It's still a relatively unexplored area. Having read that 2014 paper as part of my research, I tried to find people who'd carried it forward, and there didn't seem to be anybody really who was looking at this. Simulation hopefully was demonstrated that that's a really useful way of exploring these. And there are loads of configurations, but as we say, not all of them are stable. And in making my presentations, I created quite a few configurations where the exoplanet was just instantly ejected, which is interesting in itself because that might be how rogue planets are being formed. And that's really me done. Questions, if we want to take them now, Roger? Or
Yeah, I've got one from Siegfried here. He says, is the thesis available on the internet? You now have a very good simulator for the forward problem. Will you try to solve inverse problems and fit actual? Can't see the rest of it.
let me have a look. My chat box here.
Can you see it? Kepler something.
To infer system planet parameters. These are all areas it could be taken. I did produce this software outside of my thesis, so the software is mine and mine alone, and really on a best efforts basis. Having finished my master's, I don't have any active research projects at the moment, although I'm looking at opportunities. That's certainly an area I might like to take it. The thesis itself is a master's dissertation for the Open University, so I believe belongs to the Open University. So I'm not sure I'm able to make it available online, although perhaps Rodney would have a better view on that.
Yeah, it's a little bit of a grey area.
Yeah.
I don't have a definitive answer, but I'm pretty sure that you can. No, I'm reasonably sure, be careful what I say, reasonably sure that you can share your dissertation with others for private research.
Yeah. Okay.
But we need to make, I think we need to, I need to get a definitive statement on
Yeah.
that.
check with Ulrich.
Things have changed quite recently. There has been
Okay.
some tightening of constraints on us. So let's do that first. But what you've done is your presentation today was absolutely not surprising, because I know what you're capable of doing, but that was really, really good presentation and leaves us
Thank you.
with lots of opportunities for exploring what can be done in this area by amateurs and MSc students and PhD students as well.
Yeah.
I think we're on the verge of some interesting areas where amateurs could really do useful work. They're going to have to be pretty skilled amateurs, yes, but those people are around. More and more people are computer savvy, computer
I should
skilled.
say, although it was easy, well, it wasn't easy to put together that simulation. I was inspired by your work, Rodney, which gave me the basic idea.
Well,
but
yeah,
also, I do have a background in computing. I spent 20 years in
indeed,
the IT
yes,
sector
yes.
before changing jobs.
I
And
gave
therefore,
Paul I gave Paul a toy simulator, and he's turned it into a tool which is clearly ready for further development and then real use to solve real problems. So
well, I do hope
that's quite clear to me.
to continue some development. I've just seen a question in the chat about limb darkening and whether I could introduce it. I have looked at that, and theoretically, it shouldn't be a lot of extra work to do that. So it's kind of on my wish list for a later version to bring in limb darkening. And that would make that light curve, which is at the moment works purely by taking a 2D intersection on the screen of one circle in front of the other and reducing the luminosity, which I've calculated from the star temperatures using Stefan Boltzmann's equations, and that's good as far as it goes. But yeah, limb darkening would be really good to put in there. So it's on my list.
Yeah, indeed. I see we got Dennis Conti with us.
Yes. Can I just pop in here, Rodney? I think that was fantastic, and certainly it's something when Callum gets these all up on the internet, I'll have to work through again, as it was all a bit quick. But no, fantastic, I think there. And probably one thing worth pointing out, you may have noticed this, of course, is that the stellar eclipses tend to be more V-shaped than the planetary eclipses, which are more U-shaped. So people shouldn't get confused between the two.
Yes, very much. I should have made that point, Roger. Thank you.
Another
Rodney,
possible.
Sorry, carry on.
Okay, yes. A possible development. You're going to get a lot of suggestions for developments, I think, from participants. I think I mentioned this one to you. The idea that the orbit evolution process is going to have errors building up.
Yep.
And one way to reduce those errors, to treat them, is to say that the orbital simulations should exhibit a constant total energy in the stellar system. The sum of the kinetic energy of the components plus their potential energy with respect to the center of mass, if that has to be constant, and your simulations will build up an error in the total kinetic energy and potential energy. And you can correct that every now and again at some suitable repetition rate. You could correct that and make the simulations even more accurate than they already are.
Yeah, that's another one to go on the list, I think, Rodney.
Rodney, I was wondering whether we should break now, or I should bring my second talk forward so the afternoon speakers are not out of line too much.
Yes. So according to our original schedule of early this morning, Paul only spoke for 25 minutes.
Yeah, well,
it was a lot longer.
minutes.
It was a lot longer because that was really a tremendous presentation. Well done, Paul.
Thank you.
So let me think now. We don't want to upset the afternoon session because I think Daniel and Ashok probably are getting themselves ready for their particular times.
I can do mine now.
If you do yours, you're going to do your presentation on the system that you've been looking at. So I think that's probably the right thing to do. And then we'll get into maybe a slightly longer lunch than we predicted, but then lots of things are not as we predicted this morning. And then we can come back and stick to our original schedule. I think that's probably the best way to do it.
So from as batting at number 11, I'm now batting at number 2, right? Okay. I'll bring my second one up then, and might take me a few moments to get this thing running. So I didn't want to interfere with anything else that was going on. Right. Slideshow from beginning. Looks like we're up and running. Got an introductory page there. Everybody see it?
I think, Paul, you'll have to stop your sharing first.
Yeah, we need to take Paul's down.
Yeah, I've got all right. I'm not there yet. Okay. No. I'll have to restart here. Something seems to have played up. Just a moment, folks. Oh, I know why. It's all right.
Paul, your statement that if anything can exist, it probably does, is actually a very powerful statement of the potential for amateurs to participate. As long as they don't actually have to observe for every minute that they need to in order to see something unusual. What we need, of course, is some pattern recognition software behind people's backyard telescopes, which can be trained on interesting targets where we might expect to see something unusual in relatively long periods of time.
I should say the comment was probably better attributed to Prof. Brian Cox, who I think in one of his books on quantum mechanics says if anything that can happen will happen.
Yeah, well, we can twice use that one. That's a good one. Yeah. I think what we need is lots of amateurs with remote telescopes in very good seeing conditions, Chile and southern Spain and lots of other places, Australia, where they can train their telescopes on particular targets and literally build up lots of observing time, but not being sitting there at the eyepiece, as it were. There's a challenge. There's lots of opportunities there. Right. Which ones are practical?
My opening screen up there now.
You're good to go, yes.
Okay,
yeah, I can see that.
Okay. Right, the Kepler 88 exoplanetary system. I'm going to briefly introduce a piece of software called LC Tools. Very, very complex, but I'll only cover one small piece of it. And on Rodney's insistence, I will also cover very briefly Exoplanet Pi. Right. This is a summary of the LC Tools features. The author, Alan Schmidt, is extremely helpful, and you can get the software from him, and he's very helpful as far as answering any questions are concerned. And so this presentation will be a quick walk through the LC viewer. I won't be covering the signal finder, generator, or TTV finder. What I will do for the LC viewer is put a tutorial online explaining how to use it. Right, this is the Kepler 88 system. I'd like to get rid of that. That's all right. I got the speakers up on the side and I couldn't see half of my slide. Right, this is the Kepler 88 system. B was discovered by the transit method in 2013. C was discovered in 2013 by analyzing the TTVs of B, and D was discovered by the radial velocity method in 2020. B and C orbit very closely to their host star, much closer than Mercury does to our sun. D has a similar orbit to where our asteroid belt is situated. These variations, if I had a pointer, I would use it. Just a moment.
Pointer in the bottom left-hand corner,
Yes,
which you can
okay,
pick
yeah.
up.
Right, yeah.
It's called annotate.
These variations are caused by the interaction of planet C, which is these are variations of B, and B and C are in a near 2-to-1 resonant orbit. C has a mass of about 0.7 that of Jupiter, while B is much smaller at 0.03 Jupiter masses. The planets and their host stars, as we've mentioned earlier, orbit the common center of gravity, the barycenter, and that's this position here, obviously. The effect of the 3 planets on the position of the host star can be seen in these 3 charts with B, C, and D. Astrometric data collected recently by the Gaia spacecraft revealed the presence of 2 exoplanets shown by the motion of their host stars about the barycenter. That's this diagram on the left. In a situation where a large planet and a small planet orbit the host star as shown on the right, you might get TTVs due to the orbit of the smaller planet being perturbed by the larger one, and you might also get light time travel difference with the Earth being down here. So you might get a very small light time travel difference. You might see the TTVs. Right. Now a brief description of the LC viewer. This is what you get when you initially open it, and this is for Kepler. This is for a Kepler star, Kepler 88b. So you get this initially, and you can then detrend it. And the other thing you can do is get a phase folded signal here. There's a very useful, a quick guide which has all the hotkeys in to do each of these. So it's quite easy to use. So that's the start, that's the detrended, that's a phase folded curve. Top right is a expanded view showing the transits, and bottom right shows the transit time variation. And the analysis agrees with the paper I mentioned earlier. That is, there's approximately 24 hours top to bottom between the transits. And this shows it's +3 to -21, which is 24 hours, and the TTV period is 647 days. As you can see, they're in a near 2-to-1 resonance, and there is a formula for calculating what the super period, the TTV period, might be. You take the period of the inner planet and the period of the outer planet, and this was calculated to be 579, whereas the actual TTV period is 647. Of course, it may be that that large extra planet is influencing this. Measuring between 2 consecutive transits, you can do that, and this gives you the period, which is 10.92 days, which agrees with a known value. That's easy enough to do. Just expand the light curve I showed earlier. You can click on a transit to get the transit data, transit duration, period, radius, and so on. So it's quite easy to get that data. And you can also get the properties of the host star as shown here. And you can find signals with Lomscargill, and this shows that the period is 10.92 days, which again agrees with the known value. Finally, we've been considering some form of collaboration with the AAVSO exoplanet section. What we hope to do, is build this around a transit timing variation project with the objective of combining radial velocity and transit data to better define the planetary characteristics. This project is in its very early stages, so I can't really say any more about it at this time. But assuming all goes well, we'll hold a meeting. Well, hopefully we can get everybody together to fully define this project and invite participation, but it should be quite interesting. Right, moving on to Exoplanet Pi. Very briefly, software and user guides are available from Peter, and I found it quite easy to use with some help from him. And the main purpose of this program is to identify transits in available satellite data, study the transit time variation, and see if the planets are spiraling down or away from the host star, and see their interactions between the planets. Later releases will determine the orbit of those planets around their stars, which could give us even more information. So this is briefly what I'm going to discover: how to download data, detrend it, fit the transits, extract the timing variations, and display various plots, and look at the exoclock data for this particular planet. So this is what you get when you download the data. One sector number is one time period. Lines with the same sector number come from different sources, but you only really need to select one. So, for example, we take here these various sector 36. You only need to detect one. You only need to choose one of those, and the best ones are the SPOC or TESS SPOC. So this is what you get when you look at the light curve initially. It doesn't look very good, but when you detrend that using a feature known as Wotan, it looks much better, and you can see the actual dips there. And then, don't know where Peter gets his names from, but his facility for fitting the transport is called Batman, and you run it and you see this is the curve and this is the fit, and you need to put some data in before that to actually set the thing running. Can take some time, this, so it's best to do it before lunch or before you go to bed, depending on the situation. This is an example of the TT fitting, and you have the super period peak to peak of the transits, and this is for Kepler 18d. And this is a corner plot, which I don't fully understand, although Rodney has explained to me several times. But as long as the overs are all sitting in the middle of the boxes, it tends to suggest that you've got a pretty good result. This is a phase diagram which indicates a super period. That's the period of the variations of 17.9 days. And this is the power spectrum, which again gives you an indication of the same timing. This is the exoclock data, which shows the cyclical nature of the variations of Kepler 18d. Exoplanet Pi allows the user to choose between linear decay or periodic changes in the transit times when you're doing your analysis. Previous slides showed the periodic option, whereas this slide shows the decay option. The left planet is from Exoplanet Pi, which shows the decay in orbit, and the right plot is from the exoclock data, which indicates a possible eccentric orbit because the orbit was increasing there and then decaying there. And this bit here is the same time frame as this bit here. But a paper published in 2019 leans towards decay rather than eccentricity. Little more on the Kepler 18 system. Downloaded data shows different depths of transits. C is possibly the shorter ones, and D is the larger ones. C occur at 8-day intervals, and D at approximately 15-day intervals, which agrees with the known data. So the super period for C is given as, comes out as just under 34 days from exoplanet pi, and for D that. If you do the calculation using the formula I showed earlier, you get 7 super period of 33.8, which agrees with that. The 33.8 there agrees with the exoplanet pi number, and the 17.9 agrees with the 17.9 of D. So exoplanet pi, actually, the calculations do work out and do compare well with the calculated ones. Just check I've got that right, because it didn't make much sense there. Super period is 33.8. That's right. That's that one. And the D is 17.9, which is that one. So that's what exoplanet pi tells us, and these are what the calculations tell us. So the calculated super period does agree with the exoplanet pi data. So that'll take us up. Question time will actually be at the end of the day, not now, but as I've moved my presentation, that still appeared there. So that can take us up to lunchtime. What do you say, Rodney? We reconvene at 1:30?
I think on balance, that's the best thing to do.
Yeah, okay.
We've got Daniel and Ashok with their own particular contributions to make to this, actually what's turning out to be a really interesting session. So the question I have about what you've just been doing is that Peter is obviously not with us today.
No.
He's been in hospital recently, and I guess quite a few of us would love to get his software and start using it to really understand its capabilities now that you've introduced them. What do you think the best way to do that would be?
Well, I'll contact Peter. I wanted to ask him if he could actually record his presentation, and then we can put that up. And
That
I'll
would
ask him
be, yeah.
And I'll ask him if it's okay for you to have his email address to pass around the people who might want to use his software. And I'm sure he will say okay, and then we'll do that. So I'll contact him about recording it. I'll contact him about if it's okay to share his email address, and then you can pass it on to whoever you want to pass it on.
Yes, indeed.
Right. Okie dokie then. So we're back again at 1:30.